Hello, people. This is another enthalpy question. We're trying to find enthalpy change. So we'll just read the question. When 1.10 liters of 2.10 molarity of sodium sulfate solution at 30.1 Celsius is added to 1.90 liters of 0.7 molarity of barium nitrate solution at 30.1 Celsius in a calorimeter, a white solid barium sulfate forms. The temperature of the mixture increases to 41.1 Celsius. Assuming that the specific heat capacity of the final mixture is 6.37 joules per Celsius times grams and the density is 2.00 grams milliliters, calculate the enthalpy change per mole of barium sulfate formed. Assume the final volume is equal to the sum of the initial volumes. All right, so the first thing we're going to do is to balance the BaNO3 and NaSO4. All right, so this is what we're going to do. Balance equation. All right, we have Na2 plus BaNO3 yields to Na, NO3, barium sulfate. So we're gonna balance this. It's 1, 1, 1. All right, next we're gonna find the limiting reactant. So here the question is we're given molarity and liters. With that, we can find moles, and there we can find our limiting reactant. All right, so M1 V of Na, 2SO4 to moles, Na2 SO4 yields to moles, BaSO4. So first we're gonna do this equation. So the given is gonna be 1.10 liters times 2.10 molarity. That's gonna give us a result of 2.31 mole Na2SO4, and this we're going to multiply it times the molar-mole ratio, which is 1 to 1. All right, the next one is going to be M1V Ba NO3 2 moles BaNO3 2 moles BaSO4. All right. So that's going to be 1.9 liters times 0.700 m equals 1.3 mole barium nitrate times the molar-mole ratio, which is 1 mole of barium sulfate and 1 mole of sodium sulfate equals to 1.33 moles of NaNO3. So now what we gotta find is which is the limiting reactant, and based on our data, this is going to be our limiting reactant, BaNO3 All right. So here, the next step here is to find mass. All right. So the formula for, we're given density in this problem, and we need to add both of the volumes. But first, we need to convert the volumes to milliliters. So first, let's do that. Let's add the liters, which is 0.10 liters plus how much? 1.9, which leads us to be to 3 liters. Now we gotta convert this to milliliters, like I said before. So we gotta multiply it times 1,000, because 1 liter equals 1,000 milliliters, which leads us to be 3,000 milliliters. So the formula for mass is going to be mass equals volume times density. And guys, please don't forget your units. So this is going to be 3,000 milliliters times 2.00 grams per milliliter. Which is we're just going to cancel this out, the terms or the units, as you would like to call it. And this will leave us with 6,000 grams, or 6.00 times 10 to the power of 3 grams. All right, now the next step is to find Q. Or, in other words, find heat gain by solution. All right, so in other words, Q. So Q is composed of MCAP, or mass times specific heat times delta T. So in here, the information is telling us all the information that we need. So we already found grams or mass. So let's put everything into this formula. So Q equals 6.00 times 10 to the third grams. The specific heat is 6.37 joules over Celsius degrees times grams. And the delta T is going to be 41.1 Celsius minus 30.1 Celsius. So first, let's cancel out our terms. So grams cancels out with grams here, and Celsius, which goes along with this Celsius, cancels out with the specific heat Celsius, leaving us to just the joules. So Q equals, or is going to have 420 joules, or also known as, or written as, 4.20 times 10 to the 5th joules. And last step, guys, we're going to find delta H. And the units for delta H equals Q over moles. And we're going to be using the moles of the limiting reactant. So let's plug these numbers in. 4.2, and this will be negative. 4.20 times 10 to the 5th joules over the limiting region, or the limiting moles, which is 1.33 moles of NaO3. But remember, they're asking us in kilojoules, or I didn't, in kilojoules per mole. Sorry guys, I didn't write that. So this is going to be here. So this is going to be a -3 times 10 to the 5th joules per mole. So as we move along with this, sorry, I meant to put it decimal, negative 3.16 times 10. So we want this to be in kilojoules, and the conversion factor is 1 kilojoule equals 1,000 joules. Sorry, 1,000 joules. So here what we're going to do is multiply this by 1,000. And this is going to give us a result of negative 316 kilojoules per mole. And I'll show the work of the kilojoules, the conversion. So negative 3.6 times 10 fifth joules per mole times 1,000 joules and 1 kilojoule. All right, so we're gonna divide. So one moment. All right, so this is gonna give us a total of negative 316 kilojoules per mole. This will be your answer right here. All right, thank you.